Good morning, students. I welcome you all for another lecture on the course Digital Logic Circuits. In today's class, I'm going to discuss about synchronous counters. Basically, a counter is a sequential logic circuit. What a counter can do is it counts the number of clock pulses. There are two types of counters we have. One is the synchronous counters and second one is asynchronous counters. For this class, I'm going to discuss about synchronous counters. In next class, I'm going to discuss about asynchronous counters. So what a synchronous counter is? Synchronous counters are basically sequential logic circuits. In these counters, the clock pulse is simultaneously applied to all the flip-flops present in the counter. It can be designed for any counting sequence. That means the counting sequence may not be in a sequential order like 1, 2, 3, 4, 5, 6, not like that always. We can also design a synchronous counter for the counting sequence like 1, 3, 6, 9, 12 like this. Or we can also design synchronous counter for a counting sequence like 0, 2, 4, 6, 8 like this. Whatever the sequence if you want, for that counting sequence, we can design this synchronous counter. That is the meaning of this particular statement. And one more thing is we can design this synchronous counters for both up counting as well as down counting. Basically, this synchronous counter is sequential circuits. That means it can be designed with the flip-flops. The number of flip-flops needed for implementation of counter is the number of counts your counter has 2 power n. Then the number of flip-flops needed is equal to n. By using n flip-flops, we can count maximum counts are 2 power n. The 2 power n we can also call modulus value of the counter, or simply we can call as mod value of the counter. For example, my counter count total 8 counts, then the modulus of the counter is 8. If a counter count 16 clock pulses, then that counter I can call as mod 16 counter. And one more thing is here the number of counts counted by the counter may not be always is equal to 2 power n. Sometimes its value may be less than 2 power n. If that value is less than 2 power n, such counters we can call as truncated counters. I repeat once again, the number of counts counted by the counter is less than 2 power n. Such counters we can call as truncated counters. You should remember this. Then how to design a synchronous counter? The first step is draw the state diagram of the counter. That indicates your counter can do up counting sequence or a down counting sequence. Our first count is what? What should be the next count? That information we are getting from this state diagram. Second step is from the state diagram, write excitation table of the counter. We can basically design counters either by using JK flip-flops or T flip-flops. So based on what are the flip-flop they want for the designing of a counter, according to that, we have to go and write the excitation table for the counter from the state diagram. And step 3 is simplified flip-flop input expressions by using a K-map after writing the flip-flop input expressions from excitation table. And fourth one is after simplification of K-map, after simplification of flip-flop input expressions by using K-map, implementation of logic diagram of the counter. These are the 4 simple steps we should follow while designing of asynchronous counters. I repeat 2 things. Number 1 is this counter can be designed for any counting sequence, and we can do the counting both in up counting style as well as down counting style. Number 2 is we can design these counters either by using JK flip-flops or T flip-flops most of the times. And one more thing is a counter counts maximum counts of 2 power n, and sometimes the count value is less than 2 power n. If the number of counts is less than 2 power n, such counters we are calling as a truncated counters. and where n indicates the number of flip-flops present in the counter. Now we will see some of a synchronous counters designing. I start my discussion with a 3-bit synchronous counter. That means a 3-bit, the name itself indicates, we know that each and every flip-flop can hold 1 bit. To hold this a 3-bit, I need a 3-bit flip-flop, 3 flip-flops. So my synchronous counter should have 3 flip-flops. How to design it? We have a fixed procedure for that. In that, step 1 is making state diagram of the counter. See here, friends, this is a 3-bit. So by using 3-bit, I may get 8 different accounts, that is from 000 to 111. If my present state is equal to 000, my next state is 1, that is 001. If my present state is 001, next state is 010. If my present state is 010, next state is 011. Like that, my counting starts from a 000 and maximum count is equal to 111. That means here I can go and use all 8 counts so that it is not a truncated counter. It is a normal synchronous counter. From this, the next thing is making of excitation table. I would like to design this counter by using T flip-flops so that here my flip-flop inputs are T2, T1, T0. The present state of T2 flip-flop is Q2 and the next state of T2 flip-flop is Q2 plus 1. Present state of T1 flip-flop is Q1, next state is Q1 plus 1. Present state of T flip-flop 0 is Q0 and next state value equal to Q0 plus 1. See here, this is my present state 111, so 000. So 000 is my present state. Next state is nothing but 001, so 001. If my present state is 001, next state is 010. If my present state is 010, the next state is 011. If my present state is 011, the next state is obviously 100. And my present state is 100, the next state is 101. If my present state is 101, the next state is 110. If my present state is 110, the next state is 111. If my present state is 111, the next one is 000. So then, what is the T flip-flop inputs? The excitation table of T flip-flop. If present state 0, next state 0, obviously T input is 0. So same thing is applicable for second flip-flop. So here Q1 0, Q1 plus 1 also 0. So T1 is equal to 0. But present state is equal to 0, next state is equal to 1 only when the T input should be 1. So T input is 1. Coming to the next case, Q2 plus 1, both are 0, 0. So T input value 0. Q1 0, but Q1 plus 1 is 1. So that T1 is 1. Q0 is 1. Q0 plus 1 is equal to 0. T0 is equal to 1. That means if present state and the next state both are same, your T input is 0. If present state and the next state both are different, your T input is equal to 1. So that's what we know from the T flip-flop. Basically, T flip-flop we are calling as toggle flip-flop. That means the present state and the next state if are complementing each other, that time your T input should be changes. That is equal to 1. So like this, we are going to get the excitation table of your counter. Now we have to go and write what the flip-flop input expressions are. That should be step number 3. See here, friends. So T2 is 1 for only for the combination that is 111 as well as it is 011. So here I was considering min-term case, so that 011, so that it is M3 and 111 that is M7. So that I written as T2 is equivalent to sigma M of 3 comma 7. So here I write a T2 is a function of Q2 comma Q1 comma Q0. Similarly, T1 is 1 for 1, T1 is 1 for 3, T1 is 1 for 5, T1 is 1 for 7. So all these are the min-terms. So that T1 is a function of Q2 comma Q1 comma Q0 is equal to sigma M of 1 comma 3 comma 5 comma 7. And similarly, T0 case, T0 is all cases it is equal to 1, so that T naught is equal to sigma m of 0, 1, 2, 3, 4, 5, 6, 7. Now this expression we have to simplify by using K-map that we do in step 3. So simplification of flip-flop input functions by using K-map. For T2 case, T2 expression is sigma m of 3, 7. So that is here 3 and 7, both are 1, 1. Q1, Q0. It means here the rows are identified with the Q2, columns are with the Q1, Q0. So here I got a pair. For this pair, Q1, Q0 values are 1, 1. So that T2 is equal to Q1, Q0. For T1, my expression is sigma m of 1, 3, 5, 7. 1, 3, 5, 7. I got a quad. For this quad, unchanged value is Q0. So that T1 is equal to Q0. For T0 case, my min terms are 0 to 7. So all the cells are filled with 1. So these are forming as one group. All these are the min terms. So min term plus 1, min term value is 1. So that 1 plus 1 plus 1. And it is equivalent to 1. So T0 value is equal to 1. Now, with the help of this flip-flop input expressions, now we are going to design logic diagram. See here, friends. So this is a logic diagram for our synchronous counter 3. And a quick glance of implementation of this 3-bit synchronous counter. Step 1, designing of state diagram. Step 2, excitation table. Step 3 is K-map simplification. And step 4 is implementation of logic diagram. The same way we can go and design for 4-bit synchronous counter. First, I design the state diagram. It is again up counting. So I start from 4 zeros and I was insert 4 ones because this is a 4-bit synchronous counter. That means I need 4 flip-flops. I design this with the help of 4 T flip-flops. Again, present state, and these are the next state values. And these are the flip-flop inputs. Again, from this excitation table, we write a flip-flop our flip-flop input expressions. Those should be simplified by using K-maps. And then we are getting these type of expressions. And by using them, we are going to implement the logic diagram like this. The procedure is same what I was using for a previous 3-bit synchronous counter. And next coming to decade counter. Decade counter in the sense 10. It is a mod 10 counter because it counts total 10 clock pulses. To design this decade counter, I need 4 flip-flops because 2 power 4 is equal to 16. But out of 16 counts, I'll go and use only 10 counts. It is a truncated counter. So I was going to design a decade counter for up counting sequence so that my counting starts from 4 zeros and it is ends with 1001. Total number of counts here is equal to 10. But once you cross the value 1001, if your present state may be 1010 or 1011, 1100, 1101, 1110 or 4 ones, for these cases, your next state values are don't care. Once the next state values are don't care, then automatically flip-flop inputs also don't care. But for only remaining 10 states, we have to go and find what my flip-flop inputs are. So I'll calculate what my flip-flop inputs based on excitation table of T flip-flop. So then, next thing is the simplification of that. So these are the expressions for T3, T2, T1, T0, and their simplifications. So later, I'll go and realize the logic diagram of this with the help of these expressions. So these are my T flip-flops. The clock pulse is simultaneously applied to all these flip-flops. And with the help of these expressions, I realize this logic diagram. This is a way how we are designing a synchronous counters. Thank you for patient listening. We'll meet you on next class.